This is the first video about forces. This is the dynamics unit, learning about what makes things move the way they do rather than just describing their motion. What a force is a push or a pull. We talked about forces a lot last year, but basically the idea is the force causes changes in motion. Some examples of forces. When you're standing on the floor exerts a force on you, that's why you don't fall down, but you will also exert a force back on the floor. And if you want to prove that to yourself, one thing you can do is, with some floors at least, you can actually show that they move ever so slightly when you walk on them. By the way, we call this a normal force. It's a piece of vocabulary you ought to remember. Now you know what it means. The way forces work is that it's always exerted by some object on another object. It's the result of an interaction between two particles, and those forces can cause changes in the motion of both particles. Now, the kinds of forces you need to know about. There's gravity. It's exerted by every object in the universe. It's long-ranged, although the farther these two particles are apart from each other, the weaker it gets, but there is some gravity at any range. It can reach infinitely far. Sometimes we call it weight, and near the Earth's surface, the weight force, the gravitational force, is equal to the mass of an object times the gravitational field, which happens to be the same thing as the free fall acceleration, but we're going to call it gravitational field in this unit. There's also the normal force. It's what we call a contact force. That means it only exists when two objects are in contact. You have to be standing on the floor for the floor to exert a normal force on you. If you jump and you're no longer touching the floor no longer exerts a normal force on you. And it's always perpendicular to the surface. So when the floor is perpendicular, the normal force from the floor is straight up. Pardon me. The floor is flat, so perpendicular to that is straight up. And the important thing to remember is that that's not always upwards. If the floor is slanted, the normal force will be at an angle. There's also friction, which is another contact force. It tends to oppose sliding motion, and it's always exerted parallel to a surface. There's also tension, which is the kind of force exerted by a rope. There's spring forces, which are exerted by a spring. Go figure. Springs can either push or pull, depending on how they're stretched. And then the more the spring is stretched or compressed, the greater the force. The equation we use is F equals negative kx. The negative sign means that when you stretch a spring, it pulls back on you. When you compress a spring, it pushes back on you. K is something called the spring constant, and F is the force. That's an equation you would do well to memorize if you haven't already. You should know it from last year. There's also the drag force, which acts opposite an object's velocity as it goes through the air. And generally, the faster you go, the more drag there is. There's also buoyant force, which we did something with last year, but we're not going to do so much this year. You just need to know it exists. We'll learn more about all of these except normal and tension later. The rest of them are subtle. When you are doing a lot of these problems, you'll draw free body diagrams that show all the different forces that act on a particle. So we'll represent it as a dot. And then each arrow has its base on the dot and it points in the direction of the force. So this would be an example of a free body diagram. I don't know exactly what it is, but you've got three forces, you label them, and you've got to label them with the kind of force they are too. For this example, it's difficult to do that because I don't know what it is. But you've got normal, you've got gravity, you've got tension, you've got friction, you've got a spring, you've got air resistance, and so on. When we get to the second semester, we'll have electric and magnetic forces as well. And so here's a few examples. There's a free body diagram for a block on a ramp. We'll see this all the time, so you would do well to make sure you understand this one. So here's the block on the ramp. That angle of the ramp we'll say is theta. And we'll draw the block as a dot, and we'll ask what forces act on this block. Well, there's obviously gravity. And there's the weight force that will point straight down, Fg, or call it W. There's also a normal force from the ramp, and notice that that is perpendicular to the surface of the ramp. And if it's sitting still, well, what's keeping it from sliding down the ramp? Well, friction, which is going to point parallel to the surface and oppose the direction that it would slide if it was sliding. So there is our free body diagram. What we're going to do in problems like this is we'll usually set up a coordinate system where the x direction points down the ramp and the y direction is perpendicular to the ramp. The reason for that is that now f and n point along our coordinates, and Fg is the only one we'll have to do trigonometry on. One thing you should prove to yourself is that the angle between this new y-axis and Fg is the same as the angle of the ramp. This shows up all the time. You need to understand why that is. Now the next thing is you in your chair. This is a fairly simple one. There's you. There's a weight force on you. Gravity is pulling you down. There's a normal force from the chair that's pushing you up. And you can kind of tell from these two forces that they're equal, they balance out in a sense. So your motion is not changing, I hope, unless you're falling out of your chair, in which case the normal force has gone away. Now here's a couple others. A bird sitting on a power line. I'll draw a picture. And one thing I'm going to check tomorrow is have you drawn a free body diagram for that? And then also a book being held against the wall. So there's a book. Physics. Someone is holding it against the wall, like that, and it's not sliding down the wall. Draw a free body diagram for that as well. Label all the forces. Also for tomorrow, answer question 1 in chapter 5. Question 1, not problem 1.